Welcome to the LemnaTec Academy. In this video, I will explain what to do if your plant is not a single object after segmentation. In the second part of the video, you will learn how to deal with multiple plants in an image and how to evaluate them independently. Let's get into it. The task we use an example in this video is a bit more complicated and requires some additional tricks in the segmentation part. I've prepared a little grid as starting point, as you see here. Let's check our input images first. We like to know the parent size of the leaves without the stems. Hence, we need to be very careful to select the colors in the next neighbor color separator. This isn't perfect yet, but with the help of some morphology device, we could get a reasonable result. However, we need to get rid of the false foreground from the pod and the lower stem as well. To do the latter, we will add some region of interest freeform marker device. Here we can mark an arbitrary area as region of interest, but we can use this also as a mask of where we expect the plant to be and where not. So I will mark the allowed region for the plant. We need to give this region a name. With the help of the logical operations device, we now can eliminate all parts outside the marked region. But wait, the output pod of the region of interest freeform marker and the input of the logical operations device has a different type. Therefore, we need to add a universal converter in between them to convert the region of interest into a binary mask. We select as target binary image. In the logical operations device, we need to define which logical operation we want to apply. We could do AND, meaning only white pixels in both input and output are white in the output. We can use OR, meaning pixels being white in any of the inputs are white in the output. Or exclusive OR, meaning pixels being white in exactly one input are white in the output. We want to use the region of interest as a mask to define where pixels are allowed, and therefore we need AND. Now we need some further cleaning and smoothing of the binary mask. We add a multi-step morphology and enable subpixel accuracy. Enabling subpixel accuracy helps preserving the shape, but will need a bit higher morphological steps in exchange. First, we want to get rid of the contours of the stem. This contour is a 1 pixel wide line for the most part. Therefore, we use a 2 subpixel erosion. Now we want to get rid of the holes in the leaves. We add an 8 subpixel dilation. Finally, we have to return to the original size by adding another erosion of 6 subpixel. The result is almost what we like to see, but there are a few patches left. We can handle them using the fill areas device. As mentioned in the previous video, the default size of 20 is a bit small for modern high-resolution images. Let's try 200. This looks good. To finish the segmentation part, we need to convert this binary image into an object list using the universal converter. Even though image object list is pre-selected here, we need to open it once. But let's have another look on the object list in the universal converter. We use rainbow-colored solid objects. We have multiple objects in the image now, as indicated by the different colors in the rainbow coloring. If we want to have information about the leaves together, we need to merge them somehow. This is done by the image composition device. All objects are now merged into one object and can be measured as one entity. In order to get the usual output, we need to add, as usual, an objects writer and a loop through to manage the connections. We can now measure the usual morphological parameters for all leaves together. But what if we have multiple plants in one image? We need to merge them plant by plant, but not all leaves into one object, correct? I will demonstrate how this is done in the next example. In order to do this, I've prepared some segmentation for this image. We have a tray with multiple pots and one plant in each pot. I use here the color threshold for segmentation. I use multi-step morphology to get rid of the small false positive sparkles in the image. Finally, I convert the binary image into objects using the universal converter. You see the big plants are already one object, but most of the small ones are not. And we have a second problem. We need somehow add an identifier to differentiate the different plants found in the image. Both of these tasks can be achieved using the Vessel config maker device. This creates a special version of region of interest. At the same time, it's also the most common use case for a region of interest. By default, we have 6 positions in a 2x3 layout. However, we can change it. The best way to do it is using the MTP assistant. We have 3 rows with 5 plants in our image. Now we place the top left region of interest over the respective pot. At this point, we define also the shape and size of all regions of interest. For the shape, we have these options: circle, ellipse, square, rectangle, and freeform. Freeform is the interpolation between the other shapes driven by a parameter. A parameter value of 1 represents a diamond shape. A parameter value of 2 is a circle or an ellipse. A parameter value higher than 2 if the parameter value is higher than 2, it became more and more square or rectangle shaped. At a maximum of 99, it is virtually a square or a rectangle. I choose freeform with a value of 8. This matches the almost square shape of the pots. You can position this region of interest by dragging it at the center spot. You can change its size by dragging it at the spots at the edges. However, you may enter the radius directly in the parameter fields on the right. I choose a radius of 280 for both directions. This radius is smaller than the pot itself. In most cases, this is a good idea. This can compensate for a little jitter in the pot positions. Next, we place the top left region of interest. And finally, the bottom left region. Now you could reposition each of these regions of interest individually. However, I would not recommend doing it. You may override these regions of interest using the vessel configuration of Lemna experiment. More on this in one of the next videos. These regions of interest are named starting from A01 to C05 in our case. Names always start at 01 in one of the corners. You can select at which corner you start here. Depending on context, this region of interest might also be called wells or positions. So we have created a set of regions of interest, each covering one plant. Now we can use the image object composition device to merge the objects in each region. You might have noticed the second input port of this device. It is pushed a bit more into the device itself. This marks an optional port. These optional ports are not required for the device to work, but if they are connected, the device offers additional functionality. In this case, we can use information about the different regions of interest to merge only objects in the same region. As you can see, the different objects are merged into one object per region. All objects outside the regions are kept untouched. You may merge all objects which are partially inside a region of interest, as we did here, or only those which are completely inside. In this case, This makes no difference. The partially option has the advantage that we may choose slightly smaller regions of interest and still merge the whole plant. We need to add one more device, the image object region of interest device. This device serves two purposes. It removes all objects outside the region of interest. It has a couple of options to determine which objects are inside and which are not. We will use here the partially option for the same reason as in the device before. The second purpose is to add information to each object indicating to which region of interest it belongs. Therefore, it must be one of the last devices prior to the writer. I will explain this in more detail in the next video. Now we need to add a writer device. In this case, we need the object's region of interest writer. It has one more input port for the vessel configuration. So we have our result and can configure the result image. There's a hidden message to this video. As we have seen, the analysis expects the plants at fixed positions. You define these positions as described in this video. If plants are at a different position, for instance, the plant tray is shifted to the right, the analysis may fail. It may misassign parts of the plant to another position. That said, a small jitter of a few pixels can be compensated as I demonstrated. Therefore, it is important to place your plants always the same way into your system. With high-throughput systems, this is usually done by the machine automatically. But with laboratory instruments, which are operated manually, you have to care about it. You may use some kind of positioner to achieve this. In this video, you have learned more about working with objects for single and multiple samples. In the next video, we will have a deeper look into properties associated with these objects. See you there.